Hi guys, today we will talk about the Cuk Converter, which is this guy here. It is very similar to the SEPIC converter. The only difference is the position of this diode here. The SEPIC has the same circuit as this, the capacitor here, but here it has the inductor and then the diode. This is the SEPIC and this is the Cuk. Cuk, don't know how to call it. So how does it work, this guy? Basically, this is a topology. This is a, let's classify it. This is a topology which the output voltage can be higher or lower than the input voltage. So this is a topology like the buck boost, basically, and the equation is VO minus D 1 minus D times V in. So it is very identical to the buck boost converter. How does it work? Basically, let's call this S, the switch. When S is equal to 0, so the switch is open, let me take this picture here and let plug it here. So when the switch is open, like this, so you don't have it, the capacitor C1 is being charged by the inductor L1, and so VC1 is being charged in this way. When the switch is closed, so let me substitute it with a short. The capacitor C1 is basically connected to ground, so we can separate the circuit in this way and close it in this way. The capacitor C1, so the circuit becomes like this: C1, diode D, which now it is open. The capacitor C1 will charge the output capacitor C2, which is the output capacitance here, thanks to the inductor L2. So the energy stored in C1 goes to C2. It's very simple. Let's simulate this circuit in LTSPICE. So let's open LTSPICE and let's simulate this circuit here. As always, you have to use the input voltage V in, and let's put always the series resistance of 1 milli, just to simulate the effect of the buck capacitor of 10 micro and an ESR of 20 milli. We'll put just 2 of them so that the ESR has not much effect. And this node here, it's called actually V in, which is the input voltage. Now we will connect this to the inductor L1. Let's pick a reasonable value. Let's imagine some possible data for this. Let's use V in equal to 20 volts. Let's use possible data. V in equal to 20 volts, V out equal to minus 40 volts, and let's suppose that the output voltage, output current, it is equal to 10 amps. So the output power P out will be equal to 400 watts. This can be possible data. So let's increase the inductor as well. Let's put a MOSFET. Since it is quite high, I will suggest to put them in parallel, just to split the power. The MOSFET does need a parallel because no, it's not necessary because the current should be enough for an inductor. So now let's use the low side driver. Let's generate a pulse of a switching frequency of 100 kilohertz, no, 250 kilohertz, and a duty cycle of 0.5. Because we want to have 40 volt, minus 40 volts, we need a duty cycle which can make so 0, 50 volts, delay on nothing, rise time of 10 nano, fall time 10 nano, period on d over fs, and period 1 over switching frequency. So now you need, before going here, you need the follow emitter stage, which is made by NPN and PNP, because this voltage here will be basically generated by a microcontroller, and we probably need also a level shifter for that. But let's skip the level shifter and let's go directly to the push-pull stage, which is used to give current to this guy. It is basically a low side driver. So now you need also the power supply. So let me connect this to this. Minus 15. And let me connect this to this. 15 volts. And so now you have it what you need. Let's put a gate resistor of 1 ohm. And now we have to design the flying capacitor, which in most of the cases can be 10 micro. Let's put the diode D in the low side. Let's put a Schottky diode because it is the fastest way. Sorry, I put a silicon. This is the fastest and also the most the diode which performs better. And then let's put the other inductor L2 here, and the bank of the output capacitors, which this time will make them big. 66 microfarad, and let's put them in parallel. And finally, let's put the output current load with 10 amps. So let's give some nodes here. This is the VC node, and this is the output voltage node. Let's call it out. This is in. This is just C. And this is just the gate, so let's call G, VG. And I think that we should be fine. Let's put a transient of 10 milliseconds, and now we should be fine. Let me just use some rectangles to see exactly who is he. So this is actually the Cuk converter. Okay, and this is the low side driver. And I just did the input voltage. So let's run the simulation. Let me check that everything is clear, and 15 volts minus 50. Oh, I accidentally cut. Okay, so something is happening, it is not good. So this guy here is not conducting, basically. Okay, let me check again the parameters. Okay, here it is good. Maybe I should it doesn't make any sense. So let me put just a resistor. I can't understand why it should be 1 megavolt. Let me just put one. Okay, so I didn't know why there was such a. It wasn't make any sense. So okay, let me put just z d equal to 0.5 and let me increase the transient to 5 milli. So we can see different procedures of this simulation. First, this is the so-called inrush current. It is basically because these capacitors here are not charged, and so they need energy at the beginning of the circuit. We can eliminate this inrush current just by giving the output, just by giving this, and also to the inductors the expected steady state. So let's do this. We expect a inductor current of more or less 25 amps from here and 20 amps here. So let's write dot EC I of L1 equal to 25 and dot IC I of L2 equal to 20. So now we are setting the initial condition, we are charging the inductors, and let's also charge the capacitors. So dot EC V out or equal to, how much is this? It is 20 volts. Ah, yeah, sorry, because if the output voltage can be higher or lower. If you put 0.5, it is basically the same as the input, just with the negative sign at the end. So let's put dot param V out equal to minus 20, and we will charge these guys. Let's run the simulation again, and let's see what happens. Oh, so now I obtained the opposite effect. Because no, I this is wrong. Dot EC. dot EC V of out equal to 20 minus 20. So maybe I should put also the minus here. Strange enough that it doesn't work. Ah, okay, so now it's working. So I had to put this guy with the minus. Well, fair enough. But it is not speeding the simulation at all. Instead, it's making it worse. So this is pretty stupid. Let's cancel this because it's making the simulation stupid. It is just stupid. Let's just keep the transient and that's it. Okay, so let's keep the transient of the first. Let's keep the first millisecond and just write 1.1 milli. That's it. I honestly don't care. Let's put 3, and now we are fine. Honestly, it's not worth it's not worth the risk. So let's analyze everything now. So this is the okay. So let's go step by step. First, this is the input voltage, and as we can expect, the current here is the same as the inductor current because they are in series. The input voltage here is in resonance of the ripple of the circuit because, of course, if we toggle this capacitor here, now I will show you the effect. This effect here, the ripple effect should be increased, not so much, but let's keep them anyways. Now we see the inductor current in both the inductor currents. So there is also the triangular shape, as we always know. But let's see the current of this. It is very peculiar because in the first period, okay, so now you can see what I was talking about. Okay, so let's focus on this because it is the most important. So you see that IC3, it has this strange waveform. So it has first the same waveform as the inductor. So it has basically the same waveform as the inductor, but in two different times. So in the first time, as I said before, the current is given by the inductor L1, and so you will have the inductor and you will have this current here, this straight here. Let me announce it for you. So as you can see, you have first this, which is the current of inductor L1, and then you're gonna have this one, which is the contrary of which is the negative current of L2, which should be going like this theoretically. And that's the reason why you see a current like this. What about the current of the switch? It is very clean, and it's the contrary, or it is the complementary of the diode current, because these two are basically two low side switches, complementary switches, binary pole. Now the output voltage is kept to minus 20 because the duty cycle is 0.5. If we put the duty cycle to 0.2, so if the duty cycle is less than 0.5, the V out is less than V in. Of course, I'm talking about the absolute value. If the duty cycle instead is higher, like 0.8, it works as a boost converter. So we will call these two regions as negative VAC, and if the duty cycle is higher than 0.5, the output voltage is greater than the input voltage, and it works like a negative boost converter. negative. So it is basically like a buck boost converter, but which are the most important aspect of this? First, it has only low side switches, and basically this is the big advantage of this circuit, because low side switches are very easy to drive with a low side driver, and do not require the charge pumps, bootstrap, and everything which can really slow down your circuit. It has low side switches, and this is a pro, of course. The con of this circuit is in the con of this circuit. The con of this circuit is that it requires 2 inductors. This is a very big con because inductors are bulky, heavy, and also expensive. So as you see, if I put up a 0.8, this inductor is not more enough, and so I shall put them in parallel, because otherwise 17 amps for inductor is too much. So you should make a parallel of the two, and this circuit becomes very big. But anyway, here we are working with some kilowatts, I guess, 4 kilowatts, of course. So it is normal to think that you should put them in parallel. And now the current has been cut in half. The same for this, because you can't possibly imagine for a MOSFET to supply 4000 of amps, and also for the diode. So anyway, this is the Cuk converter, and thank you guys for this video, for following this video, and see you in the next one.